Welcome to the Explainer. So, I was recently looking into what might honestly be the single most massive contradiction in modern astrophysics. For years, we've thought of these violent, volatile stars as being completely hostile to biology, just totally dead zones, right? Well, today we are going to look at some groundbreaking new research that suggests the very stellar explosions we assumed were sterilizing planets might actually be the exact missing ingredient required to spark and sustain alien life. Okay, let's dive into this. Are we looking for alien life in completely the wrong way? We have this habit of looking for Earth 2.0, a nice, quiet, stable yellow sun with a peaceful little planet orbiting at just the right distance. But the data from the cosmos is practically screaming at us that this quiet Earth paradigm, it might actually be the exception rather than the rule. Here's a quick roadmap of how we're going to unpack this whole paradigm shift. First, we'll meet the red dwarfs. Second, we'll look at the deadly flare problem. Then, we'll see how dynamic oceans save us and how atmospheres manage to survive the onslaught. And finally, we'll get to the ultimate biological plot twist, how flares actually fuel life. All right, part 1, meet the red dwarfs, the most common stars in the galaxy. Whenever we talk about finding alien life, our primary targets are usually planets orbiting M-type red dwarfs. These are stars that are smaller and much, much cooler than our sun. A perfect example of this is our closest stellar neighbor, Proxima Centauri, which actually hosts an Earth-sized planet right in its habitable zone, Proxima b. And here is why these stars matter so incredibly much. Over 70% of the stars in the Milky Way galaxy alone are red dwarfs. Let that sink in for a second. 70%. If these M-type stars are incapable of hosting habitable planets, well then the vast majority of our galaxy is just a dead, sterile wasteland. The mathematical odds of finding any extraterrestrial life are heavily, heavily tied to whether these specific systems are habitable. Let's move on to part 2, the deadly flare problem, and why scientists have been so pessimistic. Because red dwarfs are so cool, their habitable zone, the Goldilocks area where liquid water can exist, is located incredibly close to the star. But red dwarfs, especially when they're young, are highly unpredictable and violently active. Anthony D. Del Genio from NASA's Goddard Institute laid out 3 main challenges for habitability here. First, we don't even know for sure if these planets have retained their atmospheres or water. Second, because the star is so cool, the planets have to orbit extremely close just to stay warm. And third, being in that close orbit puts them right in the firing line of dangerously high flare activity. I mean, we've literally seen flares from Proxima Centauri so powerful they'd be visible to the naked eye. In theory, all that intense X-ray and extreme UV radiation should trigger a catastrophic greenhouse effect, boil away any early oceans, and completely strip the planet of life. But here's part 3. Dynamic oceans save us. The planetary thermostat. We're now realizing that planets are actually remarkably resilient. To figure this out, scientists used NASA's Rock 3D software. It's a highly advanced planetary climate model, and they used it to run 3D global climate simulations of planets exactly like Proxima b. Instead of treating the oceans like static puddles of water, they simulated them as dynamic, flowing systems. Think of it like a giant planetary thermostat. Planets orbiting this close to their star are likely what we call tidally locked, meaning one side is always facing the blazing star, and the other side is always facing the freezing darkness of deep space. But the Rock 3D simulations showed that dynamic ocean currents act like a massive conveyor belt. They actively move the warm water from the day side over to the dark side. This prevents the dark side from totally freezing over, and it keeps the sun-facing side from boiling away. Almost every single configuration the researchers ran resulted in a planet with at least some surface liquid water. Now, for part 4, atmospheres survive the onslaught, surviving the stellar explosions. You might be wondering, okay, even if the oceans survive, wouldn't those massive stellar explosions just blast the atmosphere out into deep space? Well, a recent study used an advanced atmospheric simulation tool called ATES to test exactly how gas escapes over billions of years. But here is where everything changes. The old assumption was that frequent flares would inevitably strip a planet bare, but the new simulation data proves otherwise. It turns out that flares actually have a surprisingly modest impact on cumulative atmospheric escape. It increases it by less than a factor of 2. Even with a star going through a billion-year phase of high-activity flaring, Earth-sized planets and sub-Neptunes in the habitable zone can easily hold on to their atmospheres. The planet actually survives the onslaught. Which brings us to the final piece. Part 5. Flares actually fuel life. The biological plot twist. So we've established that the planet, its oceans, and its atmosphere can survive. But as we all know, surviving isn't the same as thriving. It turns out, if you're a plant trying to grow on an M-dwarf planet, those deadly flares aren't just a nuisance you have to endure. They might literally be your primary source of food. To understand why, we have to look at the star's quiescent state, which is just its normal, non-flaring baseline. Red dwarfs emit most of their energy in the infrared. When it comes to the specific visible photons needed to drive oxygenic photosynthesis, the kind plants use here on Earth, a mid to late red dwarf is incredibly dim. In its normal state, a planet in the habitable zone of a late M star receives over 100 times less photosynthetically active light than Earth does. It's just way too dark for robust plant life to function. Now, what's really interesting about this slide is the visual proof of what happens when a flare hits. This graph maps the irradiance of the flare star YZ Cemi. See that low dotted line down at the bottom? That is the star in its normal dim state. But look at those massive spikes stretching all the way toward the top. That is the visible light emitted during a flare. Suddenly, the darkness is completely pierced by a massive broadband injection of visible photons. And this light isn't just bright, it's practically a perfect biological catalyst. We can call it the flare photosynthesis recipe. During a flare, the star emits a broad spectrum of intense heat, a black body continuum, along with these specific, highly charged spikes of light called Balmer emission lines. Now, if you look at the chemical absorbance spectrum of chlorophyll, which is the molecule that drives photosynthesis, it has two major absorption peaks, one in the blue and one in the red. The light emitted by a red dwarf flare overlaps almost perfectly with the exact wavelengths chlorophyll needs to eat. It's as if the flares are biologically tuned to feed plants. The absolutely crucial point here is the sheer scale of this boost. When researchers convolved the stellar flare data with chlorophyll absorbance, the results were just staggering. For a late M dwarf, the photosynthesis effectiveness during a flare jumps up to 20 times higher than its quiescent baseline. For mid-M stars, a flare can boost the photosynthesis effectiveness up to 60% of what we experience on a bright, sunny day on Earth. Now, of course, there is a catch. You can't just flash a bright light at a plant for a single second and expect it to grow. The flare has to last long enough for the plant's light harvesting apparatus to physically acclimatize to that sudden rush of intense energy. A quick 1-minute burst just won't do it. But observational data shows that the most intense M-dwarf flares, the ones that pump out the most energy, can last for hours. These prolonged superflares give the alien biology exactly the time it needs to harvest the light. And this brilliantly illustrates how we have to completely rethink alien ecosystems. I absolutely love this quote from astrobiologist Mullen and Bass. The stellar activity cycle may replace the orbital period as the year. Because these planets orbit so fast, sometimes completing a whole lap around their star in just a few days, plants can't really base their cycles of growth and dormancy on the planet's orbit like they do here. Instead, their spring and summer might be entirely dictated by the internal magnetic activity cycle of the star itself. They wait in the dark, totally dormant, until the star erupts, and then they feast. So I want to leave you with this final thought. If alien biology isn't driven by the slow, steady changing of the seasons, but is instead entirely dependent on violent, hours-long stellar explosions raining down from the sky, what does a year even mean to them? We started out thinking these stars were deadly, but it turns out the violence of the cosmos might actually be the very heartbeat of extraterrestrial life. Thanks so much for joining me on this explainer, and as always, keep looking up.